In this video, I want to discuss with you some of the strategies that you can use to decide which test to use when you're trying to test a series for convergence. So there's a lot of text here on the screen, so don't be scared. Take a deep breath. I'm going to go over the main points of this with you. Whenever I'm given a series to test for convergence, there is no one test that works every time. So I have to look at the series and somehow from its characteristics decide on which test to use. This is a skill that you develop with practice, and so it's really important that you practice each test on this screen here separately. And if you try and watch this video at the very beginning without ever practicing the other ones, it's not going to make a lot of sense. It's just going to seem like a lot of memorization, and that's not what's going on. We're not memorizing this sequence of decisions here that we have to make. We're trying to, after getting a lot of practice, seeing the patterns, come up with something that works the majority of the time. So whenever I'm seeing a series and I want to test it for convergence, the first thing that I look at is, do I remember this? Have I seen this before? So that's like the step one right here. Do I see this as something similar to a problem that I've seen before, that I've solved before? Do I remember which strategy I used the first time? So that would be the first one, the first decision, the first sort of point of reflection that I'd make here. Two, if that's not the case, if I don't immediately recognize this as something that I've seen before, I will then go through these steps A through F. There's a G actually underneath, that A through G then, that I feel are a good sequence of steps to take, a sequence, sort of a mental step-by-step checklist to go through that helps you decide what to do. So first of all, looking at the series, I'll think, can I easily see that the limit of this thing, the general term, is at 0? Because if I can easily see that, then I'll use the test for divergence. If that's not the case, then I'll go to step B and think, oh, is this geometric or is this a p-series? Even if I immediately see something that looks geometric in the back of my head, I'll think, if I'm already in the step 2 here, that means I don't know exactly what to do yet. I will still think, does the limit look like it goes to 0? So I will think about things that way. If I see that it's geometric or a p-series, then I'll try using those sort of immediate recognizable tests. There's not a lot of work involved in these. But if next after that my series is not exactly geometric or not exactly a p-series, I'll consider using a comparison test. So maybe it is not a p-series or not geometric, but maybe it's similar to one. So maybe I can try a comparison test, either direct or limit comparison test. And if that doesn't work, then I'll see, do I see anything alternating here, anything that looks alternating? Now, to me, these are kind of separate. Looking at these, to me, these are one thing, B and C. So either geometric or similar, or geometric or p-series, or similar to geometric or p-series, or alternating. I'll decide on one of the two. Just sort of, maybe I could have put a decision 3 here. A, if not A, then either B or C, and then if not B or C, then D, and then after that go to other decisions. To me, these are sort of separate paths down the decision tree, excuse me. But either way, you can do what you want with these steps. This is nothing mandatory. I'm just trying to outline what I want to do, and then after this, I'm going to go over a lot of examples of each of those steps here with you. Then if it's not alternating, then I'll think, is this something that the ratio test would work well with? For example, do I see a factorial? Do I see a product of a lot of constants to the power of n? Then if I do that, then I'll consider the ratio test. If instead I see something like this, meaning something with an n to the power of n, but the something to the power of n is not a constant like this. Over here I see a constant, but if the thing inside that's raised to the power of n is not a constant, it also has n's in it, then I'll consider the root test instead, because it will allow me to get rid of this n right here. And then lastly, only if none of these work will I try the integral test. If I see something that sort of looks integrable, nothing else works, and then I'll try the integral test. Sometimes I will immediately see that it looks integrable, and then I'll decide to do the integral test, to use the integral test. But sometimes, even after immediately seeing that it is integrable, looks integrable somehow, I will not skip those steps and see if there's an easier test, because the integral test is too cumbersome, takes a long time. I have to check that the function is positive, continuous decreasing, have to integrate it after. So if there's an easier way to solve a specific problem without the integral test, I'll do it. But if I don't see immediately what to do, then I'll just skip all of those steps and then go straight to item G there. So I'm going to delete this on the screen and go through each of those steps A through G with you for several examples that I have here in my notes that I want to use. So let's do that, and at the end I'll show you all of this again, this list of tests again. Okay, let me delete this, and let's look at the tests for divergence. So what's a good series for you to use the test for divergence with? Something simple would be something like this, super easy. Whenever you see this, clearly, right, you've done a lot of limits before in your life. Since you've taken calculus 1, calculus 2 before, take limit as of an when n goes to infinity. This is clearly 1/2, which is not 0. So I can say that it diverges by the test for divergence. So when I look at it and I see the limit isn't zero easily, then I'll go and use the test for divergence. But if I look at it and I see, something like this, almost the same, but now the bottom has a power of 2, then the limit is 0 if I calculate it. So this is not a good candidate for the test for divergence. So I'll think something else. I'll still look at it and think, does the limit of this go to 0? Oh, it does. So the test for divergence doesn't help me. I'll try a different strategy. So p-series and geometric, they're kind of on the same level for me because I think they're very easily recognizable, both of them. So I don't have a preference between the two. I'll just use whatever of the two tests seems to be more appropriate to the series that I'm given. So if I see something like this, like this, is this a p-series? Maybe it isn't exactly one right now, but I can make it one with a simple change here. So it's a p-series. P equals 0.3 is less than 1, so this diverges. So this is very, very nice. Easy to recognize. A bunch of other examples here. If you see something like, even though it doesn't look exactly like a p-series or geometric, you can sort of see it happening. You can change it into one. So for example, this one here, looking at this, does it remind you of anything? To me, I can make a geometric. Again, you see this more easily with practice. But I can see this. So this is geometric. With the ratio pi squared over 5. And pi is just over 3, which means 3 squared. Pi squared is going to be more than 5. It's going to be just over 9. So this is more than 1. So this diverges. Right? But on the other hand, if I have something like this, pi to the power 2n, 10 to the power n, then this is going to be also geometric. Ratio is going to be pi squared over 10, and I don't know whether this is more or less than 0. If I have a calculator with me, I can estimate it. If I don't have a calculator with me, I can just do like 3.1 squared, see if it's far enough away. And let me use my calculator now, and that is about 9.859 over 10, which is less than 1. So it converges. All right. And then maybe I can do one more here, because geometric series are so interesting, so important. I see a -1 to the power e to the power n here. I could immediately see that this is alternating, but I wouldn't jump straight to using an alternating series test. If I go through the steps, I see that geometric series are in front of the line here. They're an earlier step, so I can see this is -1 over e to the power n, n equals 1 to infinity. And so this is, again, geometric. Ratio is -1 over e, which is less than 1 in absolute value, right? So I'll say absolute value of the ratio. This is less than 1, so this converges. So this is this is the first maybe example in which you see that following those steps is helpful. By looking at this series, right? By looking at this series, you can see that the alternating series test probably applies, because you see this -1 here to the power n. But if you go through this decision tree, this decision step-by-step guide here, you see that trying to see if it looks geometric is better, easier. Just look at how short this is. It's nothing. It's just one line of math and one line of argument. What you need to do for the alternating series test would be a lot longer. You'd have to take the bn as 1 over e to the power n, show that it's decreasing. It's kind of obvious that it is, so I wouldn't ask you to. So you got to ask what your teacher does, do the limit. So it would be a little longer, a little more cumbersome, right, than just looking at it and seeing that it's geometric. So having this decision step-by-step guide is kind of helpful. Now, if your series isn't something that you can exactly and immediately see that it is geometric or a p-series, the next step that I try and follow is I try and think if it is comparable to one. So whenever I see something that is, what can I say here, maybe a rational function. A rational function is a polynomial divided by another polynomial, or if I see an algebraic function, which would be almost like a polynomial divided by a polynomial, but now square roots are allowed. So for rational functions, polynomials can't have fractional exponents, but algebraic functions allow fractional exponents to show up. On these, I try and compare to a p-series, probably. But if I see something else, such as powers of constants that somehow I can compare in a certain way, I would try to maybe compare it to a geometric series. So let me just give you a couple of examples. So if you see something like this, let's see, n cubed plus 1 maybe. My pencil is misbehaving again today. Gotta buy a new one. Actually, this is new already. I've got to buy a new tablet. I think the tablet is, what, 2 years old? No, it's not 2 years old. It's 5 years old. Man, I got to buy another one. So if I have something like this, okay, sure, this doesn't look p-series, but it is an algebraic function, meaning it has polynomials with square roots involved, compositions of those. So this is an algebraic function. Can I make it comparable to a p-series somehow? If I sort of ignore the lower power terms, I would think that this is approximately the same as, so all of this in green goes into my scratch paper. So I go and I say, this is n cubed, 3n cubed. So this would be on my scratch paper. I'd say n to the power 3 halves, 3 and 3 halves. So it's just pretty much the same as 1/3 doesn't matter. And maybe, sorry, the bottom is not 3 halves, the bottom is just 3. It will be 3 halves later when I'd subtract the two powers. So 1 over n to the power 3 halves like this. And that is a p-series. That one that I just wrote is a p-series. And it will converge because the p is greater than 1. So to me, this looks comparable to a p-series. So I can try a comparison test with a p-series. In this particular example, I would try a limit comparison test because it's easier, but it doesn't mean that that's the only way to do it. I would try this, and then now what I'm going to write in blue is what I actually include in my solution. So all of this in green stays in my scratch paper, and then in my solution I write limit all of this n cubed plus 1, 3 n cubed plus 4n squared plus 2, and goes to infinity, still divided by, so I'm going to take this, divide it all by the series that I think it's comparable to, so 1 over n to the power 3 halves like this. I'll do some algebra, and I'll let you do this limit if you want. This is going to be, it should be 1/3, okay? Should be 1/3. You have to, step by step, to get to the place you want to take this, flip this upside down, this fraction, and then this 3 halves is going to multiply the square here. So you can bring it in, or maybe bring the n cubed out to combine with this and cancel with whatever is in there. A calculation here. I'll let you do the calculation yourself. So maybe just for the sake of clarity here, I'll show you that you need to work with those ellipses there, and then after this I'd write that since this converges, and I'll say that it's, because it's a p-series, gotta say y, p is 3 halves greater than 1, and so does the given series, and I gotta also say y. Just by the limit comparison test. So I can use the direct comparison test here however I want. I have a few more examples to show you before I go into the alternating series test. Let me just show you one because I haven't shown you anything that compares to a geometric, so something like this. Let me do this one. If I do something like the sum, maybe from 1 to infinity, and let me do 5 to the power n minus 17 over maybe a 7 to the power n plus a 9 to the power n. So even though that is not geometric, you kind of feel the geometric similarities here. If you ignore the lower terms, 5 to the power n and 9 to the power n at the bottom will definitely dominate. The 7 to the power n will definitely become large, but when compared to the 9 to the power n, when n is really large, that's not going to make a difference. So maybe I would try. I'm not saying that this will work, but looking at this, going through the steps, the bottom is bigger than the top, so definitely divergence test won't help me because I can see the limit is 0. It isn't a p-series for sure because I need n at the base of an exponent and a power, the exponent to be constant. So this isn't very similar to a p-series. It isn't geometric either, but it's comparable to one. So maybe I try a limit comparison with this series like this. I'm not saying that this will work. I'm just trying to explain what I would think when looking at this. I think it will work, but I'll let you actually think about what would happen here and decide for yourself. Now, let me talk about the alternating series test. Whenever I see something that looks alternating, if the other tests already don't apply, whenever you see something that looks minus 1 to the power n bn and 1 to infinity, then I'll consider the alternating series test, even though that's not a hard rule. Like I said, sometimes it's easier to see that it's geometric than to see that it's alternating. So I'll try something. Maybe if I see also something like this, even if the -1 isn't exactly to the power of n, maybe if it's to some power of n plus something, yeah, that's something that I'd try. So maybe let me give you a couple of examples. Maybe if I see something like, you know, a bunch of these already after seeing the other videos. Like I said, this is not a video to introduce you to all of these tests. This is a video for after you know all of the tests. But if you see something like this, then, like I said, try the alternating series test. Probably is going to work. Of course, if I see this first one in blue here, I would not use the alternating series test here. I would take the absolute value of this, and that would make it a p-series, which is convergent, p equals 3. So this blue series will be absolutely convergent, and then that implies that it is also convergent. So maybe if I see something that isn't so clear, like a slightly lower power, maybe like this. So then I have to start at 2. Then I see the -1, and maybe the -1 isn't to the power of n or n minus 1. Maybe it's to a different power. Maybe it's to the power of maybe n plus 5 or something. Doesn't really matter, because as n progresses, we're still going to be alternating the exponent of -1 between even numbers, odd numbers, even numbers, odd numbers. So this will still alternate. Now be careful with this. Sometimes things can be a little tricky. And if you see something like this, gotta be careful. Gotta be careful. This is kind of confusing. It's tricky. The alternating series test does not apply here. Take a second to think about why. The essential, look at this. The essential here is that the exponents alternate between even, odd, even, odd, even, odd, so that the power of -1 itself, the whole power, alternates between positive, negative, or negative, positive, doesn't matter. But here everything's odd. It's -1 always to an odd power, because 2n plus 1, n is integer. You double it, that's even, add 1, that's odd. So this is always, always this. And this diverges. So -1 times a p-series, that's divergent. So I would not use the alternating series here, alternating series test here. So you gotta be careful with the power of -1. It can be a little tricky at times, okay? Now the ratio test. Let me move this a little further down so I have the time space here to consider the ratio test. So if I see factorials, my immediate thought process is to consider the ratio test. Because factorials behave so nicely, if I see something like this, I did this example, I think, previously, but if I see something like this, I'm not thinking ratio test yet. But as soon as I see this at the bottom, my head immediately goes ding, 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 ratio test. Let's try it out. Maybe it's a good idea, maybe it's a bad idea, I don't know. But I will try it out at least on scratch paper, and if it works, I'll actually use that as my solution. So for this one, the ratio test actually works. I would do this, and like I said, I'll go through this kind of fast because we've done it before. So you replace n with n plus 1 and leave the fraction as it is. And then you replace, don't replace anything, just leave n as it is, and then invert the fraction to divide the two values. And the reason why the ratio test is good here is because of exactly happens with this. These cancel, you only have an n plus 1 left. So this is pretty good. These cancel, you only have 100 left in here. And these you get to combine, the other two you get to combine. So combine this and this under the same exponent of 100. So you get the limit when n goes to infinity. This will be 100 over n plus 1 over n plus 1 over n to the power of 100, right? So this is going to be 0. It's going to be 1. So this is 0, which is definitely less than 1. So this is going to converge, and actually absolutely by the ratio test. So if I see other expressions with with factorials, for example, and powers, I will try the ratio test. So a constant to the power of n is a good idea for me to use the ratio test with, because this is going to happen. They're going to cancel. N to the power of 100 isn't great because it is going to give me a 1, and 1s are inconclusive for the ratio test. But because that was only one of the things that happened and the other terms were fine, then the 1 didn't make a difference. If I didn't have this 0 here, this limit would be 1, and that would make the test inconclusive. So I try and avoid it whenever I see only these terms. For example, this in red here is something that I don't think is a good idea. So if you see something just really obvious, this is not a good idea to use the ratio test with. And this is also not a good idea to use the ratio test here. If you do, and I'll let you figure this out yourself, if you do both limits for both series that I wrote in red, both of them will be 1. So the test is inconclusive. This one converges because it's a p series p equals 3. This one diverges because it's their harmonic series. So really think about whether the ratio test is the best decision for you. When I see a factorial, I'll think about it, but also look at this. If I see, so this is n plus n factorial at the bottom here. Would you use the ratio test here? Think about it for a second. I wouldn't, because this plus messes everything up with the fraction. If you write this fraction, if you have, these are multiplying here, right? So it's okay to cancel things out, but if they were adding instead of multiplying, then it'd be super annoying to cancel things out. It's not so easy. So because these are adding, even though there's a factorial here, I would not use the ratio test. I would first do maybe a comparison. This is clearly less than this, right? Both have positive terms. This has a bigger denominator, so it's a smaller fraction overall. And this I'd use the ratio test with. So we use the ratio test here. So first I'd do a comparison and then the ratio test. So be careful. Be careful with the decisions that you make. See if they actually mathematically hold. Now this one, let's see. I have the root test a little lower. Let me organize myself a little bit in terms of space. We're almost done with all the tests. Before I try the integral test, I would try the root test. And whenever I see something that looks like this, like I said, some bn to the power n, I would consider this test. So not just something to the power n. So if I see something like 100 to the power n, or even 1 over 100 to the power n, I would not use the ratio test here. I would not use the root test here because that is a constant to the power of n. I think this is a better candidate for the ratio test. You can, of course, just do a divergence test on this one that I wrote, but I'm trying to make a point here. I would use the root test when I see something with n that's also to the power of n. So when I see n at the base and n at the exponent, I'd use the root test. So maybe something like this, something to the power of n, but in here, some ends as well. So something like this. I think I've done these examples. So I would use maybe the root test here. And I think looking at it, I think this one converges. Again, check it out and let me know. You have to do the work by the root test. I sometimes get those two confused because their names are kind of similar and they are covered in the same section of the book. But I'm talking about the root test right now. So if I said the ratio test a few times, I'd be wrong. Just assume it's the root test. Also, most of the time I use the ratio test more than the root test, especially with the sections to come, which are the power series sections. I use the ratio test almost all the time. So this is why I confused them. So you see what I said, right? There's something with n that's also to the power of n. And that I think is a good candidate for the root test. I also think we did something like this in an example. I'll start with 2 just to make it a little different. But whenever you see something like this, you see there's something with n that's also raised to a power that has n's in it. So I think this is also a good candidate for the root test. And I think this one diverges. Memory might be failing me, but again, check it out, let me know. You got to do the math. Just writing this on the side here would not be a lot of points in the test. Maybe not 0, maybe 10% of the points, 25% of the points or something. Depends on how the rubric is, but almost none of the points, I'd say. But again, something with n to the power of something with n, then I'd consider the root test. And finally, the last test is the integral test. I'm not going to use the test here in an example, but I'll show you some examples of things that look integrable. Very important here on the integral test is that this is my last resort. Because it is, again, cumbersome, I have to check that my function is decreasing, positive, and what's the other one? Continuous. And so after that, I still have to calculate an integral. So I will not use the integral test. This is my canon. This is my last resort, my nuke. Only if I see a very specific combination of functions that looks integrable, right, of expressions that looks integrable, then I will consider the integral test after looking at them and not being able to use any of the other tests. So if I see something like this, then integral test is a good idea. I can see that if I make u equals arctangent x, and du will be 1 over x squared plus 1. So this is something that looks integrable. So I think the integral test is a good idea here. But even though that's the case, I can still do this differently. I can still take the absolute values and compare this to maybe 1 over n squared, right? Maybe not 1, but maybe pi over 2 over n squared, like this, which is a p-series. So there's no one-size-fits-all strategy, but also if somebody uses the integral test here, I think this is fine. And now another variation of this, I can use an arc sine as well. Something like this you can try. Maybe try the integral test with this. And maybe something like this also. Something here that looks integrable. Again, if you go here and see this as an integral, ln x over x dx from 1 to infinity, then you can make a u sub and say u is ln x, du is going to be 1 over x. So after u substitution, this is just the integral of u du, like this, right? And this time ln of 1 is going to be from 0 to infinity, like that. So can you do this integral? Does that look something that you can, like something that you can solve? So by looking at this and seeing that it looks integrable, then I would consider the integral test here. So I think this one is fine. And I think this one diverges. But again, double check my work and actually calculate the integral to figure it out. And also, whenever you use the integral test, gotta check the three conditions. Is it positive, continuous, decreasing? So that wraps it up for this video. Again, I'll show you the list of tests that I talked about today, just for you to organize them. It's very, very important to either keep a cheat sheet of those tests with those tests on the side so you can easily choose from them. One final observation, just really to re-emphasize this idea that the integral test isn't the best test of them all, is very powerful but too cumbersome. That is the last one that we have on the list, but it was the first one that we studied. And the reason why we studied it first, or close to being the first one with these two, is that the integral test, if you don't study it first, you never see it again because you almost never use it. So really try and follow more or less this sequence, or at the very least, the thought process that I follow, and you should be fine for this type of problem.